Alright, so we want to prove this theorem directly for n equals 2, and I looked at the solution for this, and it appears that they don't want us to sort of follow the general procedure of the proof of theorem 1.3.4. This is supposed to be actually more of a bottom-up approach, where we actually check directly that this set is contained in F, rather than showing that it is. Let's see here, in the proof I believe we show that it is the inverse image of a measurable set under a continuous function or something like that. But yeah, so that makes the details a little trickier, but it's not bad. It's just that the proof looks different from the proof of theorem 1.3.4. Okay, so what we want to prove is, and I also came up with this really interesting idea. So there's this issue in this textbook that I've noticed. Well, it's not with the textbook itself, but just with notation in probability theory, it seems. There's a lot of using different scripts of the same letter. So, like, we have a lot of lowercase x and uppercase x. We have a lot of fancy S and capital S. We have a lot of things like that. And another thing is that we have element lowercase omega in the set capital omega, because x is, of course, a function from omega to r. So I was like, okay, so how can I come up with some way to say, like, to differentiate between lowercase omega and uppercase omega that would make sense? And so I'm like, okay, so let's just call it low omega for lowercase omega. So that's what I'm going to do here. So what we want to prove is we want to check that the collection of elements lomega such that x1 of lomega plus x2 of lomega is strictly less than x is a set which is contained in the sigma algebra F. Okay, so let's see here. So I claim that x1 plus x2 strictly less than x, this subset of omega is equal to the union of all elements y1 and y2 which are rational and which satisfy y1 plus y2 strictly less than x. And then we take this now we take x1 strictly less than y1 intersected with x2 strictly less than y2. Okay, so this weird formula that I've written on the right-hand side here, well, if we look at this, the set of all lomega such that x1 of lomega is strictly less than y, that's going to be an element of F because it's the inverse image under x1 of the open interval from negative infinity to y1. And so it's the inverse image of an open set in the Borel sigma algebra, of course. Well, it's an inverse image of an open set, meaning the inverse image of a measurable set in the Borel sigma algebra. And so it must be in F, since x1 is measurable. So x1 strictly less than y1, this is a measurable set. x2 strictly less than y2 is also measurable. Measurable sets sigma algebras are closed under countable unions, or countable intersections, because of being closed under countable unions and closure under complements. So we have that the intersection of these two sets is an element of F. And so we're taking a union over a whole bunch of elements of F, and this union must be countable because y1 and y2 belong to the rational numbers, and the set of rational numbers is countable. And of course, what we're really doing is we're taking the union over a subset of Q cross Q. And of course, if you take the product of two of two countable sets, you get a countable set. Okay, so we're going to prove this set. Or we're going to prove this equation. First, suppose that lomega is an element of the set on the left, x1 plus x2 strictly less than x. Let epsilon, so we know that x1 of lomega plus x2 of lomega is strictly less than x. So let epsilon be x minus x1 of lomega minus x2 of lomega, which is positive by the fact that lomega is contained in the set. And for I could be either 1 or 2, choose yi, which is greater than xi of omega, but less than xi of omega plus epsilon over 2. And since this is an open interval, if we take its intersection with the rationals, this set will be non-empty because rationals are dense. Okay? So y1 is a rational number between x1 of omega and x1 of omega plus epsilon over 2, and same thing for y2. Alright, so then for each I, we have yi is obviously going to be a rational number. xi of omega, lomega is strictly less than yi by choice. And if we take y1 plus y2, this is going to be strictly less than x1 of omega plus x2 of omega, lomega, plus epsilon over 2 plus epsilon over 2, which is epsilon. But epsilon is x minus x1 omega minus x2 omega, so this is precisely x. Okay, I think I'm just going to go back to saying omega because there's no uppercase omega here. We're not talking about it at all. So it's clear which what thing I'm talking about. All right, so there exists a y1 and y2 rational number such that y1 plus y2 is less than x, and omega satisfies x1 of omega is less than y1 and x2 of omega is less than y2. So this proves this containment because we've proven that there is some set, or there is some y1 and there is some set in this union here which contains omega. And we've shown how to get that set. Alright. So, for this inclusion, we have to take a set that's on the right-hand side. So, suppose y1 and y2 are in Q, and suppose y1 plus y2 is strictly less than x, and we're going to let omega be an element of x1 less than y1 intersected with x2 less than y2. Then x1 of omega plus x2 of omega is less than, well, x1 of omega must be less than y1, and x2 of omega must be less than y2. So this sum is less than y1 plus y2, but by assumption, this is going to be less than x. There we go. So thus, omega satisfies x1 plus x2 is strictly less than x. This proves this containment, and hence equality holds for these two sets. And that's all we need to do for this exercise. This is nice because it's a little more concrete. It shows us how to prove that this set is an element of F, but it's also more complicated than the proof given in the theorem, so it's less nice for that reason. But anyways, this is the solution, and so we are now done.